So the first inequality that we need is called the Markov's inequality. Okay, Markov's inequality. So in probability theory, inequalities are very important because when we have some experiments, these experiments, so the number of trials that we have, the number of experiments that we may have is huge, right? So we have a lot of experiments. So for example, if you have to measure the temperature like every second, right? So imagine how many data you have in 1 month or in 1 year, okay? And then you don't always want to find, so sometimes it's very difficult to find the exact value of some probability or the exact value of some function. Sometimes it's enough to find a bound. So sometimes it's good enough to know that the probability is at most 0.1, for example, right? You don't know exactly the value of the probability that you can, but you can prove that the probability is at most 0.1. That's good enough to make some decision, right? If you want to open a business or something like that, and you know that the risk that you take is lower than the 0.1 or 0.05, that's good enough, right? So inequalities are very important in probability theory. And inequalities work because we have a lot of number of trials. So we have a lot number of experiments, and then the inequalities work whenever the number of experiments that we have is very big. Okay, so look, let me write over here. So first we have to consider some random variable xi, which is non-negative. It can be 0. It can be 0. Sure. So xi is non-negative, right? So this is a random variable which is non-negative. Any random variable, so this works for absolutely continuous or discrete. Okay. Then we have to consider some random some number which is a positive, and a is a real number here. No, actually, yeah. Okay, so a is positive. A is positive. And then we can prove the following. So and the expected value of xi is finite. Okay, so we need these three conditions. The first condition is that xi is non-negative. The second condition is that a is any real number which is positive. And the last condition is that the expected value of xi is finite. Okay. So the inequality is like this. So we have that the probability that xi is greater or equal than a is less or equal than the expected value of xi divided by a. That's it. This is called the Markov's inequality. Okay. Markov, Russian, of course, about 100 years ago from Moscow State University, right? Markov is a very important name. So if for some reason you continue in probability, random processes, finance, or something like that in economics, then you will have to know, you will meet a lot this name because there's something called a Markov process. Okay, Markov process is a very important process in random processes. Okay, and if you want to study like the stock market and all of that, the stock market, this is random process. Okay, and many of the processes that you study are Markov processes. All right. Okay, so let's prove this. Very simple to prove. So look, we have that xi is greater or equal than xi by the indicator that xi is greater or equal than a. Okay, so what function is this? So look, if we have this function right here, this is a, this is xi. This is xi. What is xi by the indicator that xi is greater or equal than a? So yeah, so if xi is less than a, then this will be 0. Right? So here the function is 0. And here is just the function itself. Right? Like this. Okay, so we can see that psi is greater or equal than psi by the indicator that psi is at least a, because psi is greater right here and is equal right here. Okay, so this inequality should be clear. Is it? Yes. So maybe with a different color. We have more colors. Yeah, so whenever psi is greater or equal than a, then we take psi. This is what we are doing here. So psi here is greater or equal than a, then we take psi. But if psi is less than a, then we just have 0, like this. Okay, so the red one is psi by the indicator that psi is greater or equal than a. Okay, and we also can write that this is greater or equal than a by the indicator that psi is greater or equal than a. Right, because now we can just, instead of taking psi, we can take a. And then, of course, this is going to be greater or equal than a by the indicator.
Could you repeat that, please? The last part.
Yes. So instead of taking this, so psi, I'm going to take just a. Right? And then we can see that the red function is greater or equal than this function. This function, so this function right here are constants, are these straight lines, right? This. So here a also. So whenever psi is greater or equal than a, we're going to have a. That's it. Okay? And then we can take the expected value here in the left, in the right. And by the properties of the expected value, we know that, so from here we get that the expected value of psi is going to be greater or equal than the expected value of a times the indicator that psi is greater or equal than a. But a is constant. A is a number. So this constant, we can write it outside. So we have that this is a by the expected value of the indicator that psi is greater or equal than a. What is the expected value of that indicator? Yes, this is the probability that psi is greater or equal than a. So this is equal to a times the probability that psi is greater or equal than a. Why? Because the indicator takes only two values, 1 and 0. So this is equal to 1 whenever psi is greater or equal than 1. So we have 1 multiplied by the probability that psi is greater or equal than a, sorry. So we have the probability that psi is greater or equal than a. Okay, so from here we can see the inequality that we're looking for. So the probability that psi is greater or equal than a is less or equal than the expected value of psi divided by a. Okay, so very simple, but very powerful. So for example, in random graphs, you have been working with this. Am I right? Yeah. So yeah, so look, there's something called random graphs. Let me write over here. So most of you know what a graph is, yes? Now we will not have graphs, but random graphs. Okay, so we're gonna take some graph randomly. And yeah, so the probability that we have some specific edge is equal to p, and we have some binomial random graph. Okay, if you don't understand what I'm saying, don't worry, we don't need it. The point is that in random graphs, like, I don't know, I would say that 80% of all the results, the most important results in random graphs are because of this inequality. So you can prove it using this inequality. Well, and the next one, the Chebyshev inequality. Okay. So these inequalities are very important. Okay, very simple but very powerful. Now, this inequality is very simple, and also the bound that we have is not very precise. Okay, so the point is that there are a lot of inequalities in probability theory. Some inequalities, so the simplest one I think is this one, all right? And so why do we use the simplest one if we can use a better one? Well, because sometimes, most of the times, this one is enough. And this is very simple to use because all that we have to find is the expected value of psi. Okay. Now we have again Markov inequality. Then we will have here Chebyshev inequality, Jensen's inequality, the Chernoff inequality, Azuma inequality. All right, and we go further and further, and all the inequalities are more and more precise, but they are more difficult to apply, more difficult to find. Okay, so that's why the simplest the best. Okay, Kashibonakovsky also. Right. So, of course, Kashibonakovsky. Okay, so this is Markov's inequality. The next one is called the Chebyshev inequality. So Chebyshev was the student of Markov, of course. So yeah, so the Chebyshev inequality somehow is a better version of the Markov inequality. So let me show you that. So now here we have some random variable psi. Psi is a random variable. Such that the variance of psi is bounded, is finite. Okay, is finite. That's all that we need. So psi, we need psi to have a finite variance. Then the Chebyshev inequality is like this: the probability that the absolute value of psi minus the expected value of psi, okay, then for any a greater than 0, we have that the probability that this is greater than a is less or equal than the variance of psi divided by a squared. Okay, so this is called the Chebyshev inequality. So let's prove it. So let's prove this inequality using Markov inequality. So the probability that the absolute value of psi minus the expected value of psi is greater than a, this probability is greater or equal than a. This is the same, so we'll have a square and a square here. This is the probability that psi minus the expected value of psi square is greater or equal than a squared. So by Markov inequality, we know that the probability that eta is greater or equal than a. So we can apply Markov inequality because eta is not negative, right? So from here we can see that eta is not negative. This is a condition that we need for Markov inequality. And we can also see that we need, what else do we need? That the expected value is finite. Now, what is the expected value of eta? Is the variance of psi, exactly. So this is the variance of psi. Yeah, so here, that's why here we'll have that this is less or equal than the expected value of eta divided by a squared, but the expected value of eta is the variance of psi divided by a squared. So we have that this is less or equal than the variance of psi divided by a squared. That's it.